Okay, so our next speaker is Yusuf Ghelem from Middle East Technical University, and he will basically talk about the relation between symplectic geometry and classical mechanics. Okay, so Yusuf, it's all yours.
Okay, so hello everyone. I'd like to start my talk with some simple motivation. So when we talk about classical mechanics, like from maybe freshman courses, we always think that we're talking about maybe Rn. But in fact, most of our occurrences in classical mechanics don't happen in Rn. A simple example is a pendulum. A pendulum could be thought as S1 cross product R, and this is simply like obviously not Rn. So we'll need another geometry to explain maybe classical mechanics. So, and we call this geometry symplectic geometry. Before starting, we want symplectic geometry to obey some of, mathematically obey the Newton's laws, because we know that motion itself obeys Newton's laws. So let's start with symplectic geometry. Okay, we'll first define symplectic geometry. So in symplectic geometry, we first need a manifold. This manifold is a smooth m-dimensional manifold. So first, let's have our smooth m-dimensional manifold. M-dimensional manifold. And then we'll have some further constructions on our manifold. Okay, we want our manifold to have no boundaries. So this has without boundaries. We want a two form on our manifold, say omega, and this omega must obey some other rules. We say that we don't want omega to be, we want omega to be closed. So this means that d omega is equal to 0, where d is our exterior differential from omega k to omega k plus 1. Okay, this is the way we define d. And we want d omega to be 0, where clearly d squared is equal to 0. And then we want our form to be non-degenerate. So this will actually mean that omega x for each x on our manifold. This obviously, this is a transformation, this is a linear transformation, and we have a matrix representing this transformation. We want the determinant of this to not be equal to 0. Okay, so the determinant not being equal to 0 actually induces something else. It means that it's invertible. Okay, so this non-degeneracy actually has lots of consequences. This non-degeneracy means that our symplectic manifold must be even dimensional. And when we think about this, this is very, yes, it's a true form. Yeah, omega is a true form which satisfies all these things. It's closed, it's non-degenerate, and so on. And we want it to be even dimensional. Why do we want it to be even dimensional? We can explain this intuitionally as motion in physics is described by position and momentum. And when we think of position and momentum, we shall think of they must have even coordinates. If we're living in R3, we have 3 position components and 3 momentum components. Okay, so let's continue. Also, this the fact that it's non-degenerate, this matrix is invertible, induces the fact that the tangent space and the cotangent space is isomorphic. Tangent space and cotangent space. And we will talk about this later. Okay, so let's give a very simple example of a symplectic manifold. We can talk about our cotangent bundle. Okay, in this the cotangent bundle will later be named as our phase space in classical mechanics. Okay, where all our objects live, our momentum, our position, and so on. And we can represent this, let's call Q our configuration space. Okay, and we will take the cotangent bundle configuration space, and we'll take the cotangent bundle of Q to be is equal to M. Okay, we'll take omega as a canonical symplectic true form, which is globally exact. And because we already have theta as a 1 form on this by definition, and we can just take the exterior differential of theta as d theta is equal to omega, and omega itself will be our true form, clearly satisfying. Since it's globally exact, it will be closed obviously, and it's non-degenerate because of we have a atlas on it, a local coordinate system that can be written as, we can write in terms of theta, obviously using the Einstein summation. So, and omega can be written as space. So it clearly satisfies our what do you call it? Our first definitions we gave about our symplectic manifold, and the fact that this exists, this atlas, this mapping exists, theta exists, is also known as the Darboux theorem. Okay, so let's give another example of an orientable two-dimensional surface. Okay, we said that it's closed, but this does not imply that it's globally exact. We can give a simple example of a two-dimensional orientable surface. Let's choose any volume form on it. Let's name our surface first sigma and choose a volume form on it, omega, and then this is non-degenerate. This satisfies all the other things. It's closed, and let's assume that it's globally exact. So we're going to write to the fact that it can't be globally exact. Okay, so since it's globally exact, let's call it omega is equal to d theta. Okay, in the previous case, our cotangent bundle was globally exact, but in this case, it won't be. Why? Because we'll just use the Stokes theorem to verify this. Okay, this can simply be written as d theta, and just use the Stokes theorem to name this as theta on. Yeah, and because we said that our manifold should have no boundary in our definition of our symplectic manifold, this is automatically equal to 0, but by definition, it shouldn't. So let's give another simple example that maybe everyone can think of. A torus is a symplectic manifold. There is a symplectic geometry. A torus as T2, we can think of it S1 as cross S1. We have theta 1 and theta 2 on it as our coordinate system. Then we can take omega is equal to d theta 1, wedge d theta 2. And clearly, since it's already a two-dimensional manifold, if we take its exterior differential, it will be closed. And by the same argument, it will be non-degenerate. Okay, so as we stated before, the fact that our manifold is even dimensional has some results. It's the fact that the cotangent space and the tangent space is isomorphic to each other. Okay, and then we can the fact that the tangent space and the cotangent space are isomorphic to each other allows us to define a vector space by a contraction. So let's take X and place it in omega, leaving the first entry of omega, because omega, it eats two vectors since it's a two form. And let's place it like this. Okay, then I will not do the long algebra. We'll come to a result that this will be equal to omega ij, xj, dxi, which is a one form. Okay, so this is a contraction map. And this existence of this vector field, it allows us to give a vector field, and then we will name a vector field. We will define a Hamiltonian vector field, which we will later use in our definition of classical mechanics. We will define our Hamiltonian vector field simply as omega dot xf is equal to minus df. Okay, we will call this our Hamiltonian vector field, and the omega 2 form will allow us to define a Poisson bracket. Okay, simply as fg. We'll use this Poisson bracket in classical mechanics, because isn't classical mechanics literally a Poisson bracket, and this is obviously a smooth function on our manifold. And our actual aim is to find a symplectic geometry where we can define a Poisson bracket. And this Poisson bracket obviously is bilinear, it has Jacobi identity, and so on and so on. Okay, so let's continue. And what does this Poisson bracket actually do? It defines the change of xf along g and vice versa, g along xf. Okay, so now let's start with the relation with classical mechanics. In classical mechanics, what do we have? We have a phase space, which we can name as R2n. Okay, why R2n? I explained before, we have momentum and position. For each momentum, we have a position. For each position, we have a momentum, so it must be two-dimensional. We can name them with coordinates Q1 up to Qn, and with position components P1 up to Pn. Let me use my previous notation. Okay, so then we have dynamics on our physical system, which is a must in physics. Okay, we can express this with our Hamiltonian equations. What does dynamics mean? Change according to time. So we must take out time derivatives, use h as time, pk, and also d over dt, pk is equal to minus Hamiltonian over qk. And these are known as the Hamilton's equations. So this part is completely classical mechanics, okay? We want to somehow derive classical mechanics from our symplectic geometry. Okay, so what is h? Okay, h is something new that we described. H is the Hamiltonian function on the phase space describing the system of the energy. Okay, so in physics, we basically call h, generally in most situations, is t plus v, where t is the kinetic energy and v is the potential energy. We call it the sum of the kinetic and the potential energy. The kinetic energy, t, is proportional to p squared, and v is a function of x. Okay, it depends on the system in interest. Okay, and we have other equations that we will also deduce when we create the relation between the symplectic geometry and our the Hamiltonian vector field. Okay, so let's take the time derivative of our Hamiltonian, and it will be equal to qk h. Obviously, in these, I use the Einstein summation notation, which means that if there's a k here, I sum over k, but I just don't write it down. dtf is equal to del f over del q, del h over del pk minus del f over del pk, del h over del qk. And this should remind us of the definition of the Poisson bracket, which we'll return later on. Okay, so now let's come to the part where we will relate classical mechanics with our symplectic geometry. Okay, so we start by saying that why don't we think of R2n as a cotangent bundle of Rn? Okay, so let's think of R2n as a cotangent bundle of Rn. Okay, these are the same thing, can be thought of the same thing at least. Okay, so our configuration space is Rn, and our cotangent bundle is T star Rn, which is isomorphic to R2n. Okay, so now, as we remember, we had the Hamiltonian vector field xf of a function f, which is, let's say, we have a Hamiltonian vector field, as we stated before, xf of a function f, which is dependent on like position and momentum. So we know that by our previous definition in the symplectic geometry introduction, we can write xf as the following. Oh, sorry. Okay, why can we write it like this? Because we know that actually, yeah, since it's maybe obvious, but let's just write it. Okay, by definition, this is the same as what we stated before. So now we can apply the Poisson bracket. Okay, since we said that we have xf, we can use the Poisson bracket definition as we did before. Okay, let's have the Poisson bracket, and we can say that this is now equal to, why are we using pk and qk here? Because f is a function of them. This is the way we describe f, as we said before. Okay, so we call this, now we will talk about the canonical Poisson brackets, and maybe everyone who has some information about physics is familiar with them. If we take the Poisson brackets of like two different position components and two different momentum components, these will be equal to 0. And this should remind us maybe of some quantum mechanics. And if we take different like position and momentum of different components, this is equal to the Kronecker delta. Okay, so now we use the definition that we arrived to in symplectic geometry. In classical mechanics, we use the Hamiltonian vector field, and we viewed our phase space as a cotangent bundle. Okay, so now let's actually look at our motion equations that we wrote before, our dynamical equations. Okay, so let's look at how our position component will change with respect to time. Okay, this is just our Poisson bracket. We can write this because we can think of these are like they come from the flow of the Hamiltonian vector field, and this is the way that we can write them. So we use the fact that they come from the Hamiltonian flow. Okay, and H Poisson bracket H, okay, is clearly equal to 0. And F is equal to. Okay, so this is obvious that this is due to the flow of the Hamiltonian vector field. And now I'd like to talk about some interesting facts, maybe that we can use using like some things that we can prove in classical mechanics using the symplectic geometry definition. For example, I'd just like to state one small theorem called Louisville's theorem. Louisville's theorem actually says that our volume is conserved in our phase space. Okay, so what did we have in our phase space? We had momentum and we had position vectors. So we can think of a simple example. Let's say we have a one-dimensional collision, elastic collision. After this collision, momentum is conserved. Okay, this is just a simple intuition behind the fact that momentum is conserved. Okay, so let's state Louisville's theorem. Okay, first we have to have our volume form, define our volume form as 1 over n factorial W over n, and W over n is equal to W. And this is obviously our volume form because it's the maximum form we have, because we are on, just think of it as R2n. Omega is already a 2 form, so this is a 2n form. We can think of it at least like that. Okay, so we say that the Hamiltonian flow.
Yusuf, by the way, we have 3 minutes left.
Okay, the Hamiltonian flow phi f preserves our volume form. Okay, and how can we prove this? Okay, so the Lie derivative must be 0. Okay, and how can we write the Lie derivative? We can write it as following. Okay. Okay, so now we have to prove that the Lie derivative is 0 to prove that it's invariant, so it preserves the volume form. But we know that the Hamiltonian vector field preserves actually the omega, the form that we have. Okay, for it to preserve this form, the Lie derivative of itself must be 0. So each component here is 0. Since each component here is 0, our final answer is again 0. So this proves the fact that our volume form is preserved in our phase space. Okay, so let's continue with further arguments. Why did we use this symplectic geometry with classical mechanics? Because we actually, from here, discussions continue to geometric quantization. For geometric quantization, we start with pre-quantization. And with pre-quantization, we actually, what we do is, ones who maybe took classical mechanics, quantum mechanics, know something called the correspondence principle. We try to take everything we have in classical mechanics and apply them in quantum mechanics. So we actually want to have a function that takes f in our classical domain to qf in our quantum domain. And how do we achieve this? We want a few things in pre-quantization. We want it to be linear. We want to take identity to identity, and we want to have we want to take our commutation relations we have in quantum mechanics to we want to match them with our Poisson brackets. Okay, but then this argument continues, and we use symplectic geometry to we actually do geometric quantization on symplectic manifolds. So this is my discussion for today, and thank you for listening.